Hi, my name is Armin Nikar Shirazi. I'm a physicist and a philosopher at the University of Michigan, Ann Arbor, and I'm going to give a talk now entitled Existence in Spacetime and the Lorentz Transformations. This is a talk that I originally gave at the Midwest Relativity meeting in October of 2019. I decided to give it again online because I recently uploaded another talk online entitled The Heisenberg Interpretation of Quantum Mechanics, and it turns out that the main result of this talk that I'm giving now is actually in the background of the other talk that elucidates really what the main motivation is for the other talk. I will towards the end of this talk I'm going to discuss the connections a little bit more clearly. The papers that are associated with the talk are provided in the description. You can find a 2-page extended abstract for those who want to just, get a real quick overview of what this is about. And then the original 2 papers that introduced this and that derived the main result, entitled Dimensionality in Physics and Existence in Physics, those are also linked. Okay, so long-standing concern for me, research concern for me, has been to find a way of integrating existence into physics. Existence right now is a purely philosophical concept. It really does not make any connection to physics concepts, and that has always struck me as very strange, because it seems to me that the most fundamental aspect of any physical system is that it somehow exists. But what does that really mean? And also, if you go to any physics talk, fundamental physics talk rather, you will find that invariably the speaker will use the word existence or exists or something, some variation. And interestingly, even though they use the word, it doesn't really connect to any concepts in physics. And it seems to me as if there is some sort of an assumption about, that these are terms that are commonly understood, and that everybody understands them in the same way. But we can't really verify this because, like I said, existence does not currently connect in any way to any physics concepts. So that has been my long-standing concern, and I recently was able to make a connection, and that is what this talk is about. And it has, interesting and unexpected, and I believe really profound implications for our understanding of existence and reality. The talk that I'm giving now introduces an equivalence relation that makes this connection between existence and and physics. And the reason why this is useful is that our understanding of physical systems has become so deep and so fundamental that I believe, in order to be able to even go further and deeper in our understanding, we have to find a way to incorporate this concept of existence in our description in physics terms of physical systems. And that is what this equivalence relation does. So the main result of this talk will be really a proof of what I call the ontic equivalence relation. Ontic is a term that refers to the state of existence of something. So the presentation has 4 parts to it. First, I'm going to introduce a novel reinterpretation, or perhaps more accurately, a novel implication of the Lorentz transformations. And then I'm going to show what these implications do is they allow for thinking about special relativity in a completely novel way. And I will talk about this a little bit more, but this new way of looking at special relativity brings an attention to 4 spacetime principles that as far as I can tell, have not been previously discussed in the physics literature. And from those four principles, I'm going to then derive, or prove rather, the proposition that existence in Minkowski spacetime, as I'm going to define it, is an equivalence relation by absolute dimensionality. Now, I will discuss the meaning of this and explain the meaning of this as we go along. And then at the end, I will discuss a few of the implications, some of which I would say are pretty major. All right, so I want to start with discussion of a novel implication of length contraction. But before I go right into the details and the formal discussion, I want to give an informal feel for what it is that I'm referring to. So here's a cartoon of a cube that is length contracted in the vertical direction. And hopefully it's obvious. You can say that there's also something else going on. If you focus on the object as a whole, as opposed to just the vertical axis or the vertical side of it, you will see that the object as a whole is flattened. It has a more two-dimensional character. And it is this kind of intuitive description. This focus is not on the vertical side, it's on the object as a whole, and it's the character of its dimensionality, if you will, that is now going to that is what I'm going to focus on. So you could either say that the length contracted object has a stronger two-dimensional character, or, as it turns out in formalization I'm going to talk about, that it has a lower or lesser three-dimensional character than when it's not contracted. The term that I will be using is dimensional abatement, and basically it just says that as an object is length contracted, it attains a greater two-dimensional character. In the limit of the speed of light, the length contraction is complete, so that means that basically it goes to zero. And so when one of the sides of the object goes to zero, that means you're basically losing a dimension. And that's what I refer to, that the object is dimensional reduced. So this was kind of like the informal overview of what I'm going to now make mathematically precise. So before I go on and talk about all these definitions, I want to say something quickly about the terminology. So in the process of defining these concepts, I'm going to introduce a lot of novel terminology. And to some people that might be perhaps off-putting, but it serves a definite and important purpose. In cognitive linguistics, there's a concept called hypocognition, which refers to a situation in which it becomes very difficult or impossible to convey a concept, a new concept or an idea, when there is no label for it. So when there is no term or something that captures it, it's as if the concept is invisible. And so my purpose in introducing a lot of new terms is to avoid this, to avoid hypocognition. Obviously this only works if the terms refer to genuinely new concepts, and I believe they do. And you will see this for yourself. So my aim here is to make it easier to see that these are new ideas and to distinguish them from existing ideas, because it really requires a new way of looking at it. So considered more broadly from a more general perspective, what I'm really trying to do with also introducing the new terms is a new way of looking at an old subject. So special relativity is a subject here, and it has been around for 115 years as of now. And it's special relativity tends to be mathematically easier than many other areas of physics. And because it's so relatively old, and because it's not that difficult, it might be easy to think, it might be tempting to think that we already know everything about it that is to know. And as I hope I will be able to show, that is not true at all. It still has some interesting implications that people have not considered. And this new terminology that I'm introducing is in part meant to reinforce that there are some really new ideas that are involved in this discussion. All right, so let's now go on and start the formal discussion of dimensional abatement. So absolute dimensionality is the first thing that I'm going to define. It's a dimensionless natural number that refers to the independent length dimensions of an object. This is something that colloquially we would just call dimensionality. But I need the qualifier absolute because I'm going to shortly distinguish this from another concept, dimensionality concept. Volume boundary ratio is a ratio of a compact object. Compact here means closed and bounded, with an absolute dimensionality greater than 1. So it's a ratio of the object with absolute dimensionality greater than 1, and it's a ratio of its n-dimensional volume to its n-1 dimensional boundary. So concretely, in the case of 3 dimensions, the volume boundary ratio is a ratio of the volume of an object to its surface area. The next definition is of relative dimensionality, and that's the other dimensionality concept I was talking about. This is also dimensionless ratio, but it's a ratio of ratios. It's a ratio of the volume boundary ratio of a compact object with dimensionality greater than 1, which is our comparison object, the objects that we're interested in, to that of a reference object. Now, there you can see the mathematical expression. In the numerator, we have the comparison object, the object that we're interested in the numerator of the fraction of fractions. And in the denominator, we have the volume boundary ratio of the reference object. And this will give us a dimensionless number, by the way, a real dimensionless number between 0 and 1. The next concept is what I call dimensional diminution. So that refers to a situation in which the relative dimensionality of an object compared to what it was before is decreased by a factor that is between the open interval of 0 and 1. Now, why is the interval open? If the relative dimensionality is 1, that means the object has exactly the same volume boundary ratio as the reference object, so it's not dimensionally diminished at all. And if the number is 0, then that means it's so much diminished that basically one of the dimensions has disappeared. And I reserve for that situation a separate term, which I call dimensional reduction. So that defines a situation in which an undimensional object has a decrease of its absolute dimensionality to n-1. So in the concrete case of 3 dimensions, if you go from a 3-dimensional object to a 2-dimensional object, in the cartoons that you saw of the cube, if the vertical side of the cube was completely length contracted, it would go to 0. Then you would end up with a square, with a 2-dimensional square. So the cube would be dimension reduced to a square. So dimensional abatement now then is basically an umbrella term. It's a less specific term which can either refer to dimensional diminution or to dimensional reduction. Now, after all these definitions, I can now easily prove a proposition that Lorentz contraction can be conceptualized, or that it implies dimensional abatement. And specifically, what it means is that for speeds less between 0 and the speed of light, it implies or signifies dimensional diminution, and for speeds equal to the speed of light, it implies or signifies dimensional reduction. The proof is very, very easy. So consider an arbitrarily shaped body, compact body, that is moving in some reference frame S, and in another frame that is moving in which that body is at rest. And we imagine that this body is made out of infinitesimal cubical volume elements. And without loss of generality, we're going to orient the elements so that the direction of contraction is normal to one of the sides. That makes the calculation easier. And it's very trivial then to show that for any Lorentz contraction, the each cubical volume element becomes dimensionally abated. So if you want to verify this for yourself, here's a situation. You take a cube and imagine that you contract one of its sides by 1/2 of what it was before, and you can easily calculate this and find out that its volume boundary ratio becomes reduced by a factor of 3/4. And so this always holds, and because it's true for every volume boundary, for every volume element, infinitesimal volume element of the body, it will hold for the body as a whole. And that's it. So basically, Lorentz contraction implies dimensional abatement. So that takes care of our new way of looking at length contraction. What about time dilation? So the key point here is to reinterpret time from an external parameter. So we're conditioned, I think, both from our immediate sensory experience, but also from non-relativistic physics, so from Newtonian physics. We're conditioned to think of time as this thing that is out there, this external parameter. But there's another way of thinking about it, and that is of thinking of it in terms of the duration of existence of an object in space-time between two space-time events. This is most easily understood if the two space-time events have the same spatial coordinates. The space-time events you can think of as points in space-time that are specified by 4 coordinates, 3 spatial coordinates, and 1 time coordinate. And when the two spatial coordinates for two space-time events are the same, so what you're talking about is then just the same point in space over, different moments in time, over a time interval. And so now, instead of thinking of it as a time interval where time is an external parameter, you imagine that there's an object there at that location, and that this time interval is really tells you how much this object has existed for how long the object has existed between those two moments. So it's really, really like this reconceptualization of time it underlies everything else that I'm going to talk about. So if this is not clear, you should maybe take a moment to reflect on this. This is really, really important. That is at the foundation of everything else that follows. So I'm reinterpreting time from an external external parameter to something that really becomes like a property of an object. Its duration of existence in space-time. Now, it turns out in special relativity, there are 2 different time parameters that correspond to time. One is proper time, and that is reinterpreted as the observed duration of existence of an object in spacetime between 2 spacetime events. And in this case, now the 2 spacetime events don't have to refer to the same location in space. It can be separated in space. And the coordinate time, which is reinterpreted as observed duration of existence of an observer in spacetime, or a class of clocks that are at rest with respect to the observer. So here again, this constraint, this restriction to just not moving, referring to the same point over an interval becomes important, because the observer cannot ever move relative to himself. The observer is always with respect to himself in the same spot. So that is where the difference comes in. And the overall term that I'm going to use, which is kind of the counterpart to dimensional abatement, is what I will call ontochronic abatement. Again, from ontic, pertaining to existence, chronic from chronos, time. And what it says is that an object is, as an object is time dilated, its duration of existence in spacetime between two given spacetime events is diminished, and in the limit of the speed of light, where time dilation is complete. So by that I mean, again, if you probably heard this, right? If you could hypothetically accelerate a clock to the speed of light, which is physically impossible, but let's say hypothetically you could do this, then what you would observe is that the clock no longer ticks, and so that there is no passage of time. Translated in this new way of thinking of time as duration of existence, it would mean that its duration of existence, its observed duration of existence, would be 0. So let's now go from the informal overview to actually trying to formalize it. Before I can actually introduce new definitions and so forth, I have to talk about a criterion for physical existence in spacetime. So, like I said, my aim is to connect the concept of existence to physics, and in order to do so, I have to give some sort of a criterion for that has to be satisfied or not, that will tell me whether something exists or not. And the criterion that I have come up with is, so this is an existence criterion, and it basically just says that a physical object exists in Minkowski spacetime if and only if it is characterized by a time-like spacetime interval. So if and only if means that the implication goes both ways. So that means a physical object exists in Minkowski spacetime if a physical object is characterized by a time-like spacetime interval, then it exists in Minkowski spacetime, and if it exists in Minkowski spacetime, then it is characterized by a time-like spacetime interval. Now, this is a fundamental assumption, and this is the only new assumption that I'm making. Everything else that I'm talking about in this talk is already contained in special relativity. There's really nothing new in terms of fundamental assumptions. There are new ways of looking at things and new ways of recognizing implications of what we already know that we didn't recognize before. But other than this criterion, there is no other new assumptions. This is the only new assumption. And it is absolutely necessary because in special relativity, in standard special relativity, there is no concept of existence. And that is exactly the point that I'm trying to get at, right? So in order to be able to treat existence like a physics concept, I have to put in some sort of an assumption about, what it means for something to exist in space-time into it. I can't get around to it. And that's what this criterion does. And because it's a fundamental assumption, I can't really derive it from anything else, but I can give plausibility arguments, and I will give 2 plausibility arguments so that it seems more sensible that this really should be an existence criterion. The first one is that proper time is, or is a spacetime interval, or a time-like spacetime interval, is Lorentz invariant, and so that already makes it a good candidate for a criterion that has significance with respect to existence or ontological significance. We normally think of only those properties that are Lorentz invariant as being quote unquote real, and it's never really in standard standard physics. It's never really explicitly explained. What do you mean by real or whatever. It becomes kind of circular. By real, we mean, of course, Lorentz invariant, right? But here, I can now connect this, right? So by real, I'm talking about a property of something that exists in space-time, that in a physics sense. So Lorentz invariance is definitely very desirable to have for a criterion, and this criterion refers to a Lorentz invariant quantity is a time-like space-time interval. Another plausibility argument is that is to look at, in what ways something could fail to satisfy the criterion. And there are three ways that something could fail to satisfy it. Something could have a space-like interval. And so when an object is characterized by space-like intervals, that means it's associated with a speed greater than the speed of light. And we consider at this time such objects to be unphysical. Now, there are some speculations about maybe particles that might be traveling faster than the speed of light. They have been called tachyons. But at present, we have absolutely no evidence that there are any tachyons or that tachyons exist. So that's good. That means, like if tachyons existed, then it would mean that our criterion failed to capture some objects that existed, and so that would be a problem. Another way that something could fail to satisfy as a criterion would be if it's not recognized by a space-time interval at all. So there are things that we can colloquially, or in a maybe broader sense, broader than physics, we think of as existing, such as maybe thoughts, feelings, qualia, or even platonic objects, like numbers and things like that. And none of these can be associated with a location, in space or in space-time. And since you can't associate them with a location, you can also not define any kind of interval. So all of these are basically excluded, right? All of these you are excluded from consideration for this criterion for physical existence. And that is something that seems also very desirable. And then we get to the third way of how something could fail to satisfy the existence criterion, and that is if it is associated with a light-like or null interval. Objects that are associated with these kinds of intervals are a speed of light objects. So objects that are characterized, any object that is characterized by the speed of light is associated with a null or light-like interval. And this is a really interesting situation. I'm going to postpone the discussion of this until more towards the end of my talk, because it also highlights the profound shift in how we're looking at these objects at present versus what this suggests how we should look at them. So stay tuned for that. Okay, now that I have got the preliminaries out of the way, I can now give some definitions. First, I want to formalize the existence criterion in terms of a function which I call the spacetime ontic function. This is a map that takes me from the set of all physical objects that are in the domain of physics to the set to the set containing 0 or 1. So first of all, a little bit a note on the symbol. The reversed E that you can see here is a symbol that is used in logic as an existential quantifier. So for example, when you want to express the idea there exists an X such as that and so forth, this is the symbol you would use, and it seemed very appropriate to use as a symbol for this function. The subscript S is used because this is really an indicator function, and S is a subset of the set of all physical objects in the domain of physics. The subset of those objects that satisfy the existence criterion, so that exist in space-time. And so that means that the space-time ontic value of an object is determined by, if it satisfies the existence criterion, its space-time ontic value is 1. And if it fails to satisfy the existence criterion, its space-time ontic value is 0. Another term I'm going to define is ontochronicity. Again, from ontic, pertaining to existence, chronicity from chronos, time. Ontochronicity is a quality of having a duration of physical existence. The next concept I'm going to define is relative ontochronicity. So this is the temporal counterpart to relative dimensionality. And it's a dimensionless ratio that of the observed duration of existence of an object compared to the observed duration of existence of a reference object. And usually we take the reference object to be the observer. So you can again see the mathematical definition, which is exactly the counterpart of the mathematical definition of relative dimensionality. So the situation in which we are interested, I mean, you could, in principle, apply this to, let's say, two objects that are moving at different speeds, for example. But that's not what we're interested in. We're interested in really time dilation. And for time dilation, the denominator will turn out to refer to the observer. And so that means that the denominator will be coordinate time. The numerator will be the observed duration of existence of the object of interest, and so that will turn out to be the proper time. So as a result, for the specific situation in which we are interested, the mathematical definition reduces to just tau over t, where tau is a proper time, t is a coordinate time. And notice this is very similar to the inverse Lorentz factor, which is d tau over dt. And there still is a difference. The inverse Lorentz factor is really a rate. It's a rate of aging, rate of observed aging of an object over the rate of aging of the observer. And whereas the relative ontochronicity is just a ratio of time intervals. So there's still a difference, in the limit in which the rate of aging is constant, then they become, numerically the same, but they're not, in general, they're not the same, even though they're very similar. So the next concept I want to define is what I call ontochronic diminution. This is the decrease of the observed duration of the existence of an object in a given time interval by a dimensionless factor in the open interval between 0 and 1. So why are 0 and 1 excluded? Well, if it's 1, then that means that the proper time is equal to the coordinate time, so the object is at rest with respect to the observer, and it's not ontochronically diminished at all. So for that reason, it's excluded. And if it's 0, then that means its proper times the numerator is 0. And we already know this is 0. If it's 0, then that means that the space-time interval, or the proper time is 0. If the proper time is 0, that means that the space-time interval associated with it is null or light-like. And again, I will reserve for that a separate term, which I call ontic reduction. And the reason is when the space-time interval is null or light-like, then that means the object fails to satisfy the existence criterion, so it falls in a different category. I call this ontic reduction in exact analogy to dimensional reduction. So ontic reduction is the reduction of the ontic value, the space-time ontic value of an object to 0. And then finally, the ontochronic abatement is used as an umbrella term that can either refer to ontochronic diminution or ontic reduction. So with all these definitions in place and concepts, the space-time ontic function and all that, and the existence criterion, I can now present an easily proved proposition that relativistic time dilation can be conceptualized in terms of, or implies, ontochronic abatement. And more specifically, it signifies ontochronic diminution for speeds between 0 and the speed of light, and ontic reduction for the speed of light. Now, the proof for this is really trivial, because all it involves is substituting the terms, substituting ontochronic diminution for time dilation for the intervals between 0 and c, and ontic reduction for time dilation for v equal to c, and it just falls out. So there is not really much to prove here. It's very obvious once you substitute the terms. So the whole point of doing this was not just to show that special relativity has still some new tricks up its sleeve, even after 115 years, but when you focus on dimensional abatement and ontochronic abatement, what you're doing is you're really looking at special relativity or at special relativistic concepts from a completely new angle, from a completely new way, in a completely new way. And this new way then also brings attention to some principles that before, they might have been there in front of our nose, but we might not have really noticed them. And the four principles are what I'm going to then derive. I'm going to derive the Ontic equivalence relation from these four principles. So the four principles are two invariance principles and two symmetry principles. The first one is what I call the invariance of absolute dimensionality. It basically says that the absolute dimensionality of a compact body is invariant under spacetime coordinate transformations. I hope this is obvious. The Lorentz transformations are basically rotations in space and Lorentz boosts. And obviously, rotating a body or boosting it to speeds less than light, obviously, because the Lorentz transformation is not defined for a boost to the speed of light. The number of dimensions that characterize the object are unaffected by that. And I put space-time coordinate transformation instead of Lorentz transformations because this is actually more general. This also refers to the Poincaré transformations. The Poincaré transformations are basically the Lorentz transformations plus translations. And you can see that translations also leave the number of dimensions that an object is characterized by unaffected. So I hope this is obvious. This is probably too obvious, and my suspicion that these principles have not been, as far as I know, discussed in the physics literature before is, my suspicion is that it just seemed too trivial, like this is so obvious, not worthy of mentioning. However, once I discuss some of the implications of the Ontic equivalence relation, which I derive from these four principles, you will see that it has some consequences that are not trivial at all. So stay tuned for that. The next principle is a symmetry principle, and I call it the homodimensionality of space. And it says that the dimensionality of every maximally dimensional space-like hypersurface of Minkowski spacetime is everywhere the same. So I mentioned maximally dimensional space-like hypersurface because since we have 3 dimensions of space, it's possible to define a 1-dimensional hypersurface as 2-dimensional and 3-dimensional. But only the 3-dimensional corresponds to our physical perception of space. We can always, of course, define a 2-dimensional slice of a 3-dimensional spatial region, but this is more of a mathematical construct, whereas 3-dimensional space really serves as a model for reality. And so when I say maximally dimensional, I'm trying to pin down a description of space that fits exactly that fits reality, as opposed to being some mathematical abstraction or as opposed to being a mathematical abstraction. And I'm mentioning Minkowski spacetime because obviously that's the setting of special relativity, although I will also discuss very briefly at the end that these principles can be generalized to other spacetimes as well, but for the sake of clarity and simplicity, I'm going to restrict myself for now just to Minkowski spacetime. The third spacetime principle, so the third and fourth are the temporal analogs of the first and second. The first and second refer to space and length. The third and fourth refer to time. So the third principle says that what I call the invariance of spacetime ontic value is that the spacetime ontic value of any compact body is invariant under spacetime coordinate transformations. This can be proved directly from the fact that the spacetime ontic value is defined in terms of proper time, and proper time is Lorentz invariant, and we know that Lorentz invariant quantities are invariant under spacetime coordinate transformations. The fourth principle is what I call the homodimensionality of time, and it basically says that the dimensionality of every time-like hypersurface of a Minkowski spacetime is everywhere the same. So the homodimensionality principles say that space everywhere is three-dimensional, and time is everywhere one-dimensional. And we can connect this to the Lorentz transformations by considering that the Lorentz transformations can never take us, can never take the description of a three-dimensional object to a description in two dimensions, right? Because in order to change the dimensionality, the one way to do it would be if you could transform it to the speed of light, which is impossible. So there's no Lorentz transformation for that, and so the Lorentz contraction basically obeys this. And by an exactly analogous argument, the Lorentz transformations, yes, they can result in time dilation, but the time dilation can never be so much that the proper time becomes zero. And so time dilation also obeys the invariance of spacetime ontic value. As far as the symmetry principles are concerned, this is obeyed because we know that these transformations always take us from 3+1 slicing of spacetime to another 3+1. You never have a situation where a transformation takes you, Lorentz or Poincare transformation takes you from 3+1 to 2+2 or something like that. If that was possible, that would violate the homodimensionality principles, but it's not possible. So the transformations obey the homodimensionality principles. So, as a preliminary work to proving the Ontic equivalence relation, I want to make two observations. The first one is that the two invariance principles couple absolute dimensionality to spacetime ontic value. So what does that mean? What do I mean here? Recall, in the standard way of looking at special relativity, length contraction is always coupled to time dilation. You can never have one without the other. And in this reconceptualization that I had introduced, dimensional diminution and ontochronic diminution also become coupled in exactly the same way. What the principles do is they extend this further to not just cover diminution but also reduction, so that you have this coupling over more than one, more than within, just like, let's say, if we're talking about three-dimensional space, just in three dimensions. It actually extends it. The two homodimensionality principles ensures that this coupling that I just talked about doesn't just hold in particular regions of space-time, but over all of space-time. And so, if you had a space-time, for example, such that the maximally dimensional space-like hypersurface was different in different regions. So a space-time, let's say, there was 3+1 in some parts, and 2+1 or 2+2 in other parts. What would happen is, this coupling between the ontic reduction and dimensional reduction would no longer hold if you go inside the region versus outside the region. But since you don't have this, the coupling holds everywhere. So those are the two ideas that underlie the derivation of the proofs that I'm going to give in a moment. To make this simpler to understand, just for convenience, I'm going to define another term, isodimensionality, So a spacetime is isodimensional if and only if both its time-like and its maximally dimensional space-like hypersurface are homodimensional. So clearly, Minkowski spacetime is isodimensional because everywhere, the spacetime can be decomposed into 3+1 and not, in a physical sense. Of course, mathematically you can do whatever, but I'm talking about like in a physical sense. Everywhere the transformations take you from one 3+1 slicing to another 3+1 slicing. Okay, so now we have everything to prove the following proposition. Physical existence in Minkowski spacetime is an equivalence relation by absolute dimensionality. This is what I call the Ontic equivalence relation. So I'm going to go through the proof step by step, even though it's really, really simple. This is an easy proof. So first, remember that an equivalence relation is determined by three properties: reflexivity, symmetry, and transitivity. So let's consider an object A, which is n-dimensional, and we're supposing that it obeys the four principles that I just discussed. And by the coupling of spacetime ontic value to absolute dimensionality, it must exist in an n+1 dimensional Minkowski spacetime region. And by the isodimensionality of Minkowski spacetime, that region is actually all of the spacetime. And now we can show that it satisfies these three properties. So A exists in the n+1 dimensional Minkowski spacetime in which it exists. That's really that's really obvious. I don't know how much deeper to prove this, but that is exactly what we mean by reflexivity. To prove symmetry, consider another object B, which is m-dimensional. And, the same thing that we said about A applies here as well. So it exists in an n+1 dimensional spacetime. Now we suppose that in order to prove symmetry, we suppose that A exists in the same spacetime as B, but that means that n+1 is equal to m+1, so n is equal to m. And so that means that B has the same number of dimensions as its absolute dimensionality is the same as A, and that in turn implies, by the previous arguments that I just gave, that it exists in the spacetime that is the same spacetime as the one in which A exists. And that proves symmetry. And transitivity is proved exactly in the same way. I actually let you do this as a little exercise because this is just so simple, everything here. It's surprising how mathematically this is not challenging at all, I think. But what it requires is a new way of looking at things, a willingness to integrate new ideas like existence into physics, and I think these were the barriers to trying to recognizing this earlier. I feel so many times, I think the majority of times, the barriers are mathematical difficulty or things like that. But in this case, it's interesting. It's something very different. All right, so let's now talk about the implications of the Ontic equivalence relation. It has profound implications, as you will see in a moment. An equivalence relation basically divides a set into what are called equivalence classes. Equivalence classes are subsets of a set in which all the elements of the subset are related to each other by the equivalence relation. And since the equivalence relation here divides, objects that exist in a n+1 dimensional spacetime by their absolute dimensionality, you get what is called a partition of the set of objects in physics by absolute dimensionality. So depending on how many what dimensions, what their absolute dimensionality is, that determines in which spacetimes they exist, and in which spacetimes they exist determines how many dimensions they have. And so to illustrate this, like visually, I gave this little diagram which shows a partition. So in our 3+1 dimensional spacetime, by the Ontic equivalence relation, there can only exist three-dimensional objects, which is something think about it. Up until now, as far as I know, it seemed more or less like an accident that, the number of dimensions of the objects in space always match. That seems like a curious accident. It turns out it's not an accident at all. It is it is a direct consequence of the four space-time principles that I mentioned, that I discussed just a moment ago. And so it kind of, I think it really gives us a little bit of greater insight at a most fundamental level about our existence in space-time. So now I'm going to talk about speed of light objects. Remember, I had earlier in a slide I had mentioned I'm going to postpone the discussion about how, if an object fails the existence criterion because it is characterized by null interval or a light-like interval, and we're here now. Now I'm going to talk about this. So basically, once you understand the Ontic equivalence relation, it's obvious that speed of light objects have to belong to a different Ontic equivalence class than spacetime observers. So Ontic equivalence class means an equivalence class based on its nature of existence, essentially. So speed of light objects exist, if you will, in a different way than spacetime observers. And you can use this as an explanation for why it is impossible to transform to a speed of light frame, a rest frame. If you could transform to a speed of light rest frame, well, what would happen is you would be no longer a member of the same Ontic equivalence class as all other space-time observers. You would no longer be a space-time observer. And so what this really brings out is this notion that it is possible for something to exist without existing in space-time. This is a radical idea. I can't emphasize enough. And this became especially clear to me when I discussed this with several physicists, and I have always run into the same problem. When I first mention this, people have difficulty understanding this because the assumption that, if something exists, it has to exist in space-time, or if it exists in space-time, that means it has to exist. That the two basically are synonymous, that saying existence in space-time is like redundant. You can just say whether something exists or not. That this is so deeply ingrained that when you actually try to convey the idea that it is possible for something to exist, even if it doesn't exist in space-time, they have difficulty understanding it. I've run into this now in my personal experience discussing this with other physicists several times, and every time I have to go, and try to break this down, and I'm not saying by saying it doesn't exist in space-time, I'm not saying that it doesn't exist. I'm saying that only that it doesn't exist in space-time. This is, I think, a consequence of our conception of, really a consequence that we have not, as far as I can tell, earlier tried to incorporate, our concept of existence, or try to understand how it relates to physics. So now, when I'm trying to do it, we're at such a advanced stage in we have such a deep understanding of physical systems, so that now, when at this late stage, now I'm trying to incorporate, this concept of existence, it brings up this, this radical change. So it is possible that what the Ontic equivalence equation, Ontic equivalence relation implies is that it's possible for something to exist without existing in space-time. This is a radical idea. This is this is one of those, the word paradigm shift is unfortunately overused quite a bit, and but I think in this context it is absolutely appropriate. And one of the indications, like I said, is that I see is in the reaction of physicists who are for the first time exposed to this idea. They don't even understand it. I have to actually talk about it in many different ways from many different angles before they actually get it. And so that's why I'm belaboring this part also in this talk, because from my personal experience in talking to other people, so I'm taking the time to really hammer this point down. Now, it turns out that special relativity, standard special relativity, actually gave us hints that this was the case. So, like I said before, if you consider the duration of existence of a speed of light object, let's consider a photon. From the moment that a photon is observed to be emitted to the moment that it is observed to be absorbed somewhere else, so there's time that passes for the observer. But for the photon, if you could describe it as in terms of like what it would be like for a photon, no time passes because its proper time is 0. And that implies that its duration of existence between those two space-time events, the moment it came into existence and the moment it went out of existence, is 0. That means in its frame, if you want to talk hypothetically about this frame, in its frame there's the same frame. There's the same moment. The moment it came into existence and the moment it went out of existence are the same moment. And this seemed within the context of special relativity, this seems like a really strange coincidence, that people just dismiss as, I once had I asked a famous relativist, unfortunately he passed away a few years ago, but I asked him about this. What do you make of this? And he was just a dismissive hand gesture. He said, "Oh, that's just philosophy. It's not taken seriously." But now there's an explanation. The reason that the duration of existence in space-time between any space-time events, including the moment they come into existence and the moment they go out of existence, the reason that it's 0 is because they don't exist in space-time. They exist, but they don't exist in space-time. Another hint was that 4-volume, you cannot obtain a 4-volume by integrating a 3-volume over in the light-like direction. And so that is another indication. So, if something exists in space-time, you should be able to characterize the space in which it exists, our 4-dimensional space-time, by integrating 3-dimensional space in the direction in which it is, quote unquote aging. It's not aging if something travels at the speed of light, but when you try to integrate it in that direction, in the light-like direction, you get 0. So that is another hint that special relativity gave. Another hint, and this is probably the most obvious, is that no space-time observer, or more generally, no space-time object can transform to a speed of light rest frame. That should have been the first hint, right? So if no space-time observer or space-time object can transform to the speed of light rest frame, that is a hint that speed of light objects are not space-time objects. So, and in fact, I think in 50 years from now, 100 years from now, probably, when people say, oh, some student who's just learning physics, who's just beginning to learn relativity, special relativity, and they ask, oh, why don't photons or speed of light objects exist in space-time? I think the answers they would get would be something like, oh, because no space-time object can transform to the speed of light rest frame. But despite all these hints, special relativity couldn't come out and really tell us that speed of light objects don't exist in space-time, because there is no concept of existence in standard special relativity. Remember, I had to put this in via the existence criterion. That was the one assumption I had to put in the additional assumption, so that we could go from indirect hints to a direct statement in terms of the Ontic equivalence relation. And so if we accept the notion that speed of light objects exist, but they don't exist in space-time, the natural question is to ask, well, where do they exist then? And we can answer this question, right? So speed of light objects are completely length contracted. That means they're dimensionally reduced. In our case, that means you go from 3 dimensions to 2 dimensions. And by the Ontic equivalence relation, that means they have to exist in a 2+1 dimensional space-time. And so to basically denote its repository of existence, which is different from our repository of existence, to promote it to a physical entity of its own, I will call this area time. So especially in general relativity, but not just in general relativity, also in high energy physics, people use 2+1 space-time as a toy model to test out various ideas, and the underlying understanding behind that is, oh, this is not reality. This is just a toy model. This is a simplification. It's a mathematical abstraction. We're just using it so that we can describe in a simplified setting. We can explore some ideas. And remember, I'm trying to get away from I'm trying to avoid hypocognition. So I'm trying to get away from this way of looking at 2 plus 1 space-time. By the Ontic equivalence relation, 2 plus 1 space-time, there is such a thing. It's part of the reality. It's not part of the reality that is accessible to us, because we exist in 3 plus 1 dimensional space-time. So that is the part of reality, if you consider by reality like this broader thing of things, that might be just in the domain of physics. But nevertheless, it is just as real as area time would be just as real. 2 plus 1 space-time would be just as real as 3 plus 1. And to denote this, I'm giving it its own term. So again, this goes back to my effort to avoid hypocognition. Now, the mathematics of special relativity actually already gave us some hints. So for the hint I want to discuss, it would be easier if you could just imagine a space-time diagram. Imagine that you have an object that is moving, located momentarily at the origin. If you compare the space and time axis, you would find that, in a sense, the space and time axis of the moving object would be scissoring in. They would be approaching the diagonal, which is the light-like direction, and the faster the object is moving, the closer the time, the more the time and space axis, the space axis being the axis of that indicates the direction of motion, and I'm assuming a standard configuration, so where the object is moving from left to right in the diagram. So the time and space axis would be approaching the light-like direction, and they would get ever closer with higher velocities. In the limit of the speed of light, the two axes would merge with the light-like direction. And if you think of Minkowski space-time as a vector space, then one of the basic ideas of linear algebra is that when you have two directions that are basically the same in a vector space, then or vectors that point in the same direction, then the vector space is actually linearly dependent. And that indicates that in such a frame, in a frame, that if you could associate a frame with the speed of light object, in such a frame, our spacetime, our 3 plus 1 spacetime, has too many dimensions. It has one too many dimensions. Now you could go from 3 plus 1 either to 3 plus 0 or to 2 plus 1. But there's another hint in special relativity which tells us that for a hypothetical frame that moves at a speed of light, all of space is compressed into a plane, which means that there are only two independent space-like directions, or as physicists like to put it, two independent space-like degrees of freedom. And if you only have two independent space-like directions available, then it can't be that the space is a 3 plus 0. It has to be 2 plus 1. And it's really interesting that special relativity, right from the beginning, from over 100 years ago, had this hint, and we didn't see it. We were completely blind to it. There is a philosopher and historian of science who originally was a physicist by the name of Thomas Kuhn, who actually noticed this and lucidly explained it. The problem is that in our current paradigm, this whole notion that you can assign a frame to an object that moves, that is associated with the speed of light, just doesn't make sense. And so we were completely blind to this. And what Kuhn noticed was also that as you when you're within a particular paradigm, it's very difficult to notice ideas that are key, perhaps, that are found in the next paradigm. And the scientists are it's ordinarily very difficult for them to see them at all. Most often we're just blind to them. Now, in the beginning, I mentioned that the reason that I uploaded this talk is, or decided to redo this talk, is because I recently uploaded another talk on quantum mechanics entitled The Heisenberg Interpretation of Quantum Mechanics, and that this talk would provide some background on a fundamental assumption. And here I'll just take a moment to explain what I meant by that, because now I can say it. The fundamental ideas that I'm pursuing, now I don't really mention this in the other talk either, it's just kind of in the background, but the fundamental idea I'm pursuing is this, that there are objects that are two-dimensional by the Ontic equivalence relation. They cannot exist in space-time. They have to exist in area-time. But under some circumstances which still need to be described, elucidated, understood, and for which we only can at this point label our ignorance by attaching a label to it and calling it a measurement. Under those circumstances, an actual space-time object, so an object that exists in space-time, where exists is exactly the criterion that I'm using as used in this talk, emerges. And because it's possible that so the fundamental idea here is that because it's possible that there's more than one possibility usually open for a space-time object to emerge, when there's no measurement, our best possible description of such two-dimensional or lower-dimensional objects is in terms of what space-time objects could emerge out of them. And so what you have is then a description in terms of a combination or superposition, if you want to call it, of space-time systems that only exist as potentialities. Now again, I didn't, in my other talk on the Heisenberg interpretation, I never actually addressed the question why I'm so motivated to describe quantum objects in terms of potentialities. That is a key point. This idea that quantum systems are potentialities. But here the reason for that was, as hopefully it's obvious, I couldn't just say, oh, it's because they're manifestations of lower dimensional objects, because then I have to explain all this other stuff, which took me an hour to explain here. So, but now I can say it. So the reason why I think that quantum systems only exist as potentialities is because I believe they're space-time manifestations of lower dimensional objects. And if you're more interested in seeing the details of that worked out, I strongly encourage you to also watch my other talk on the Heisenberg interpretation. So the last thing I would like to now discuss very briefly is how the Ontic equivalence relation can be generalized beyond Minkowski spacetime. In my proof of the Ontic equivalence relation, I explicitly assumed Minkowski spacetime, but it's easy to see, I hope, that it should not be too difficult to generalize it, at least to some significant subset of the spacetimes that are treated in general relativity. Now, why is that? Because when you, in general relativity, basically you start with defining pseudo-Riemannian manifold that has a metric defined on it, and it turns out that already gives you, contained within this way of defining, or the starting point, is already this notion that the manifold is isodimensional. In other words, that a 3 plus 1 slicing, if you're talking about now a 3 plus 1 manifold, takes you, from one frame to another, or under any of the transformations that we normally consider rotations, boosts, and even translations. So, and if the spacetime is isodimensional, then we already know that the two homodimensionality principles hold. Now, the invariance principles are not, it seems to me, as explicitly contained in there, but it seems to me that we also assume those, because if we didn't, it would become noticeable. We would notice it when these invariance principles are violated, because it would mean, if they're violated, it would mean that we have a space-time on our hand in which it is possible to say that whether something exists in that space-time depends on the observer, or whether it's three-dimensional or two-dimensional or whatever depends on the observer, assuming that the coordinate systems that you use doesn't change dimensions either. So because it seems just so obvious that it should not violate these kinds of invariance principles, I would say ordinarily it's not that difficult to generalize. But there is one caveat. And also, so if the invariance principles hold, if isodimensionality holds, then the equivalence relation follows automatically. But there's one caveat. And the caveat is that in general relativity, there are spacetimes that have singularities. And at least for point-like spatial regions, the generalization of the Ontic equivalence relation is nearly trivial. So all you need to do, I believe, is to relax the definition of isodimensionality to isodimensionality almost everywhere, which means that which defines a spacetime to be isodimensional up to a measure zero interval. And I believe that ensures that even though the principles may not hold at the singular points, and therefore the Ontic equivalence relation may not hold at the singular points, it holds everywhere else. And it's fairly trivial then to modify the proof with this relaxed definition, so that you can say that the Ontic equivalence relation holds in all the non-singular regions. So, in this talk, I presented the Ontic equivalence relation, which connects, remember my original aim was to connect the concept of existence, which is currently purely philosophical and has no connection to physics, to connect it to physics, and express it in terms of physics concepts. And then I derived from the Ontic equivalence some pretty major consequences. Now, the Ontic equivalence relation is easy to derive, easy to understand, I believe. But like I said, it has very profound implications for most fundamental understanding of reality. And the reason why I would argue that it should be taken seriously is, number one, it's based on one of our best tested theories in all of science, special relativity. It's derived from 4 principles, which you can check. They are not just intuitive and self-evident, but the principles, the transformations of special relativity are consistent with them. They obey them. And the mathematical derivation is also very straightforward. So for all these reasons, I think it should be taken seriously. Now, there is, of course, always a sociological aspect to these kinds of things. So when a physicist who's already well known, well recognized, presents a new idea, it's very often taken seriously faster than when an unknown physicist does this. But really, in an ideal world, it shouldn't matter. What should matter is the content, and how solidly justified it is. And I just gave 3 reasons, which I think are pretty solid reasons for taking this framework seriously and for taking, the implications, the ontic equivalence relation and its implications seriously. So thank you very much for listening, and I wish you a wonderful day.